Welcome back friends for another edition of quantum field theory and quantum entanglement. We have been discussing the quantization of the electromagnetic field. We had tried, we saw the various difficulties in quantization of the electromagnetic field, mainly because of two reasons. Mainly because one is the gauge freedom. Essentially there is a large number of degrees of freedom. The Lagrangian has large amount of degrees of freedom which the Maxwell's equations of motion cannot push or fix essentially, and this is essentially the main reason, essentially the gauge degrees of freedom, and the mismatch between the physical degrees of freedom essentially. So, physical degrees of freedom. So, the physical degrees of freedom are essentially two polarizations of the photon, whereas the Lagrangian has 4 degrees of freedom. So, this leads to a lot of problems essentially when we are trying to quantize, like the way we try to quantize core scalar fields essentially. So, we are trying to quantize 4 components of the mu field, essentially A0, A1, A2, A3, but the actual there should be only 2 of them essentially. So, this is a problem. Then we looked at various possible gauges. So, the ones we looked at are Coulomb gauge, Lorentz gauge, and then there are axial and other gauges. Okay. In this case also, and then we try to quantize it everything in terms of the Coulomb gauge quantization in terms of Coulomb gauge. Has the advantage that this quantization of the Coulomb gauge has the advantage that uh, the physical degrees of freedom are directly manifest. Directly manifest. Okay, but it has its own problems, right? What we have seen is that it is not Lorentz, it is not manifestly Lorentz invariant. Okay, it is not manifestly Lorentz. That is one bad thing about it, and if you want negative feature associated with the Coulomb gauge. So, today we will try to do the same thing with the Lorentz gauge essentially. So, it is not manifestly Lorentz invariant, the Coulomb gauge, and also it has some other issues, like for example, when one calculates higher order corrections, it is not very helpful, it is not very useful, but there are cases in which it becomes very useful essentially. In some cases, okay, this is not a very generic statement, but there are some cases where the Coulomb gauge is very useful also in calculating higher order correction. So, let me just say this is in quotes, do not take it fully accurately, but okay. So, there are some cases in which Lorentz Coulomb gauge is useful, okay, but except that you lose your manifest Lorentz invariance. So, today what we will do is that we will do quantization in a manifestly Lorentz invariant gauge, which is the Lorentz gauge. So, let us do quantization in this particular gauge using the quantization condition. Okay, using the quantization condition, which is del mu a mu is equal to 0. Okay, so uh, but there is a small trick we impose. We follow. We do not impose the Lorentz gauge condition till the last step, essentially in some ways. Okay, of the calculation. So, this is a small trick we use. Essentially we keep it as though that is this trick, unlike in the Coulomb gauge where you start imposing right from the beginning. In this case, we will say that we will postpone the use of this gauge condition until the last step. Okay, good. Okay, so let us start with the Lagrangian. Okay, Lagrangian L is equal to minus 1 by 4 mu nu, but then I will also add this term 1 by 2 del mu a mu whole square. Okay, let me just add this term. Okay, from this what happens is the equations of motion are, okay, this term will not change anything, essentially this term will not change anything. So, I can add this term to the Lagrangian, but what does it do? It slightly modifies the equations of motion. So, what we have is del mu f mu nu plus del mu a mu is equal to del mu a mu is equal to 0. So, this is the box, essentially box a mu is equal to 0. Now, just to revise you, what is the equation of motion we were using in the earlier case? Essentially in the earlier case we were using the equation of motion in the Coulomb gauge, essentially. So, we were using the equation of motion as only the equation of motion for the 3 component spinor, essentially, which is del mu a bar is equal to 0 in Coulomb gauge. Okay. So, because A0 is 0 and everything. So, now if we put this makes our life much easier, and we can do it completely in terms of a manifest manifest Lorentz invariant way. Now this is the most, not the most general form. Essentially the most general form of modification is of the Lagrangian is equal to L minus 1 by 4 f mu nu minus 1 by 2 alpha del mu a mu whole square. Okay. Now you can choose alpha to be arbitrary. Okay, and then you can solve for it and use the equations of motion and everything. Now choosing the 2 particular interesting choices are when alpha is equal to 1, alpha is equal to 1, which is the one which you are using, is called Feynman gauge, The other one is also called alpha is equal to 0, that is called the Landau gauge. So, this what does it make this now this changes the modifications of equation of motion in such a way that you end up having this particular equations of motion where all the four components have box A mu is equal to 0, have the equation of motion. Because the equation of motion is equal to del mu, so all the fields, all the components of A mu including A 0 are now dynamical. Okay, so we will just assume, let us not impose the condition again, again repeat, essentially repeat, impose the gauge condition later on and go ahead with the quantization. So, now for the present let us say that all the components of A mu including A 0 are non diagonal. I will see how to deal with it later. So, pi 0, now we can have pi 0 is equal to del L by del A 0 dot, this is equal to minus del mu A mu, and pi I del L by del A I dot is equal to del I A 0 minus A I dot. Okay. Okay. So, now this earlier this, remember pi 0 is equal to 0. Now, because of this new term pi 0 is no longer 0, and so you have a non-zero pi 0 here. Okay. Now, this comes from the new term from here, essentially we have this alpha or 1 by 2 pi alpha, the same thing alpha. Now, alpha we have chosen, this is all in Feynman gauge. So, in Feynman gauge you have this relation. Now, the point is that now because of this thing A 0 is not pi 0 is not 0. So, you can go ahead exactly like imposing equal time commutation relations like for each scalar field. So, for pi 0, pi I and everything which are non-zero. So, you can impose this equal time commutation relations. Now, okay, we will impose the gauge condition a bit later on, and when we are okay, equal time commutation relations for each of the components of the A mu field, essentially each of the component of the A mu field, each one behaves like a scalar field essentially. So, pi I. So, what we have, so let us impose equal time commutation relations to quantize the A mu field in you want to quantize the A mu field in Lorentz gauge essentially. So, you have pi for the same thing, pi nu of x, this all should go to 0. It commutes, the a's commute with each other and the pi's commute with each other. So, that is the first thing, but now you also have the main thing essentially a and pi okay. So, this is our important relation. Okay. Now we impose, unlike now you see the quantization conditions, they are all Lorentz invariant quantities essentially. So, the quantization conditions are completely Lorentz invariant quantities. So, you have a mu, a nu, eta mu nu, it is this manifest Lorentz quantities essentially. Okay, they are manifestly Lorentz invariant quantities. So, this, okay, now given this one can we can, or this can lead to, this leads to the expansion in terms of creation and annihilation operators. Okay. Now, in the Coulomb case we use three polarization vector, dimension 3 polarization vector. Here you had to use 4-dimensional polarization vectors. So, we have a mu of x epsilon mu lambda of p. Now, we have the creation and annihilation operators a p of lambda e power I p dot x, okay, plus a p of lambda dagger e power minus I p dot x, okay. So, a mu of x is equal to this. So, this lambda mu nu is with lambda mu of lambda of a given momentum has mu is equal to, so 0, 1, 2, 3. So, there are 4 polarization vectors essentially. Okay. So, there are 4 polarization vectors. Okay, good. Now, what about pi mu? Lambda is equal to 0 to 3, okay, epsilon mu on the top of lambda of a momentum p, again a lambda p bar e power I p bar dot x minus a p bar lambda dagger e power minus I p dot x. Okay, note this carefully, there is a relative minus sign, but the I does not carry a minus sign essentially. So, okay, now this, okay, now the point is that, so the main thing is that A0 has a negative kinetic term essentially, and this will whether we massage it by putting this term into the Lagrangian, whatever, at the end of the day A0 has a negative kinetic term. So, this will start reflecting itself soon essentially as we put the expansion and everything. Now, we will say that uh, the creation and annihilation operators, okay, should satisfy the, meaning the creation and annihilation satisfied, you put it back into the commutation relations essentially. Now putting back these expansions, in the equal time commutation relations, we have, you end up having the same, meaning the relations as follows. Okay, we have a lambda p a q lambda prime dagger, okay, is equal to minus eta lambda lambda dagger prime delta cube p minus q. Okay. Now other commutation relation vanishes essentially. So a p lambda a q lambda prime is equal to a p dagger lambda a q dagger lambda prime is equal to 0. So the other commutation relations vanish, but a dagger commutation relation should give me this eta lambda lambda prime. What is eta lambda prime? I will just come in a second essentially. Meaning this creates a negative. We will see what happens if you have a negative. We have already seen it. This we have seen this particular case of negative in the eta in the commutation relations once. We will see, we are seeing it again essentially, we are seeing it again. Okay. So now what are the four polarization vectors? So before defining eta lambda lambda prime, we need to know what are the four polarizations vector, because the eta lambda lambda prime will be that. The four polarization vectors are, so such that epsilon 0, epsilon 1, epsilon 2, epsilon 3. There are these four polarization vectors. Okay, we pick, this will be like time like, okay, and epsilon 1, epsilon 2, epsilon 3 are space like. Okay, so now we have to say what this lambda polarization vectors are essentially, because then you need to have so lambdas are what, lambda is equal to 0, 1, 2, 3, right essentially. So so there are, because there are four polarization vectors. Okay, I should have defined, oh did I do, okay, one second, maybe I did an overcounting of, yeah. So lambda should be equivalent to 0, 1, 2, 3 also, this polarization vectors. So there are four component polarization vectors, there are four of them because there are four polarization vectors. So there is epsilon mu 0, epsilon mu 1, epsilon 2, epsilon 2 mu, epsilon 3 mu, essentially there are four of them. But so we choose epsilon 0 to be time like and epsilon 1, 2, 3 to be space like. These are four polarization vectors, each of them is four vectors. So this is the space time index, this is the polarization index. Okay. Now what we have to say, essentially we have to pick a normalization such that epsilon lambda dot epsilon lambda prime is equal to eta lambda lambda prime is equal to eta lambda lambda prime. So that means they are orthonormal, So the epsilon 1 would be 1 and other ones are time like, essentially all the other ones will have negative things essentially. Now this will also mean that epsilon mu of lambda, epsilon nu of lambda prime, eta lambda lambda prime is equal to eta mu. Okay. Okay. So now why does it come? Because you have a now you can take eta lambda lambda on both sides essentially, and that gives me this one essentially. So it is eta mu nu. So we have to get if you take the eta mu nu on both sides, you should get back eta mu nu. So that is the main concern essentially, that you should these polarization vectors, though they depend on momentum, at the end of the day they should be given this. They should give you back the form to be unity, meaning they are all normalized essentially. Okay. The polarization vectors of course are momentum dependent, okay. So the time component is mod p, and which is nothing but the energy, and the p is nothing but the momenta. So what we choose is for the two space like for the two space like polarization vectors, we choose epsilon 1 epsilon 2 to lie transverse to the momentum. So that means you have epsilon 1 dot p is equal to epsilon 2 dot p is equal to 0. So if the direction of momentum is essential, okay. And the third one is a longitudinal polarization. So if p has a direction 1 0 0 1, then we have epsilon 0 is equal to 1 0 0 0, epsilon 1 is equal to 0 1 0 0, epsilon 2 is equal to 0 0 1 0, and epsilon 3 is equal to 0 0 0 1. Now you can see that epsilon 0 is time like, these two are perpendicular to p, whereas this is longitudinal. Okay. Now we are introducing a polarization vector which is explicitly longitudinal. Okay. No, but good thing is that there are all Lorentz invariant. Okay. Now you may question entire choice essentially saying that your these are not completely the physical degrees of freedom, obviously, right? Essentially these are not physical because you have a longitudinal polarization essentially. Now as we will see, we need a trick to of course this will lead to problems, obviously this will lead to problems, but there is a trick to get out of this problems, as we will see soon essentially. So now this, now you see this, they are all very nice looking, but the moment you put in back into this uh, uh, the commutation relations, you have a minus sign. Obviously, this is a pain. Okay. Okay. So, to be more explicit, for space like, okay, for space like, for space like polarizations, you have AP lambda AQ bar lambda prime commutator is equal to delta lambda lambda prime 2 pi cube delta p minus q. Lambda lambda prime is equal to 1 2 3. So, there is no problem, there is no negative sign. But then if you consider the time like case, a p 0 a q bar 0, oh, this is a dagger, essentially there is a dagger. Okay, this is equal to minus 2 pi cube delta cube p minus q. Okay. Now, this is very odd, and the moment you see the minus sign, we have all red flags essentially. Okay. So, these are all red flags. We have seen these red flags earlier. Okay. Also, in the case of fermion quantization, essentially, if we have states with negative norm, what it typically means is that negative sign in the commutation relations, what it typically means is that uh, you can take a Lorentz invariant, if you take um, the vacuum essentially, you and create a particle on it, it can keep creating it, or if you annihilate the vacuum on it, it can keep annihilating it continuously, and you end up having states with negative norms essentially. So, you have you can define, essentially we can define the vacuum, Lorentz invariant vacuum, by A P the lambda acting on 0 is equal to 0. You can define this thing, then you can try to create one particle states also from this essentially. Okay. So, we can create one particle states essentially, say let us say P of lambda is equal to AP lambda dagger acting on 0. So, this gives me momentum states. Now, for lambda is equal to 1 2 3, this is fine. Okay. But for lambda is equal to 0, but for lambda equals to, we have this unusual situation, we have P bar 0, Q bar 0 is equal to 0. So, you are taking a norm of these two states essentially, 0 AP acting on 0, AQ bar 0 acting on the vacuum. This is equivalent to minus 2 pi cube delta cube P minus Q. So, this means that the state has a negative norm. So, that means states with negative norm means negative probability. Okay. And this does not make any sense, and the reason is in our Lagrangian L is equal to half a bar dot square minus half a0 dot square. So, this the kinetic term of a0 is negative. So, this has a wrong sign, and that is precisely the reason why we have half the states, meaning okay, 1/4 of the states which are negative norm, and other 3 states are essentially positive essentially. Okay, other 3 states are well behaved. So, okay, to summarize, what we have done so far is we have just gone ahead and quantized um, in the Landau gauge. We have not imposed the gauge condition yet, and then we have just gone ahead written the Lagrangian in this particular fashion, where we added this term 1 by 2 del mu a mu square. This will make the mu field a0 field also dynamical. Then we imposed equal time commutation relations which are Lorentz invariant, and then we did the expansion in terms of the polarization vectors and a dagger. We derived the went to go ahead and we saw that the AP dagger operators have negative norm for the time like states. Essentially the time like states have negative norm, whereas the space like states have positive norm. So, this is, and this can be traced to the fact that the term we added in the Lagrangian has already a negative minus sign, negative sign for the kinetic terms for the A0 essentially. Okay. Now, we have not imposed the gauge condition so far. So, we will now impose the gauge condition and see what happens. Okay. Now, but still that will not be sufficient, as we will see there are several things which we have to go ahead. So, let me stop here, and in the next class I will see what are the resolutions for this problem which we have seen essentially. So, the Landau gauge in some ways follows the fermionic quantization condition, because quantization problems exactly because it also introduces negative norm states essentially, and then we will see the resolution for it and why we want to make sense out of this gauge, because quantization in this gauge, because we want to use this gauge in our physical applications essentially. Okay, we want to use this Feynman gauge in our physical application. Okay, let me stop you, then I will continue in the next lecture. Thank you very much.